All right, so welcome back to Biostats. This is Module 8A on Chapter 8, the chi-square goodness of fit test. Okay, let's imagine we're looking at a problem like, does the age of the driver affect the probability of a minor car accident? So there's a lot of potential data types that you could use to address this type of problem, and as we're going to see in this course, the type of hypothesis test we run depends on what data is accessible to us. And so let's imagine that some researchers have access to a large database. They basically know the following facts. We're going to assume this sort of without error. Um, and you can do this if you have, an enormous database. You can basically assume there's no sampling error. They know that of the percentages of licensed drivers broken down by age, well, they're not, given information on the exact age of every driver. It's just these bins or categories. So under 24 years, 16% of the licensed drivers are under 24 years old. So we could write that as the fraction in group 1 is 0.16. In age range 25 to 44 years, there's 44% of the drivers, 27% in kind of older middle age, and then 13% seniors over 65 years old. So this is some data that is a sort of background knowledge here. And that's not what not what we're going to base our hypothesis test on. These are not the data we're using to test whether or not age affects the accident rate. Down here is the data that they're going to use. They're going to get a random selection of minor car accidents, and the researchers find the age of the driver that's responsible, and they record that data in these same age bins here, so that it's comparable to what they have some background information on. So we just have a data type that is age, but it's been blocked into bins. So even though it is a numerical variable inherently, it's been essentially treated into age categories that are ordinal. They have an order from youngest to oldest, but it's almost like we're taking this numerical variable and making it into a categorical variable. All right, so the first step in hypothesis testing is to state your questions in terms of null and alternative hypotheses. And, we have to play around with these sometimes and try to figure out what fits our data, what fits the test. It's got to be true to the hypothesis we're interested in testing, but also got to be accessible to our data. So we might think, okay, well, it's the probability of getting in a minor accident is the same for each person, regardless of each age. So that's probabilities for all 4 age groups are equal to each other. And that would be compared to an alternative that the probability of getting in a minor accident differs among the age groups. So at least one of the values is different from the others. So they're not all equal to each other. Note that, we're not saying they all have to be distinct. It's just at least one has got to be different is the alternative, because that covers every possibility other than the null being true. Well, this isn't exactly the setup I gave you. This is people in accidents. You might say, well, they actually have data for being the responsible driver in the accident, so maybe that's another set of proportions, probability being the responsible driver. But we don't actually track each individual, and so it's hard to know what their probability of being in an accident is. They just have data on the accidents themselves and the age of the drivers. So that makes it hard to actually estimate a probability when you don't have the failures, you just have some successes. Okay. However, if this sort of core concept is true, then we should be able to make some statements about the expected number of accidents. So for instance, the expected number of accidents with person 1, age category 1 being responsible, the expectation for the number should be whatever our sample size of accidents is times the fraction of people in that category, or the number of sample size of accidents times the true population proportion of people in that category, right? And so the idea is that we can get a sense of what the expected numbers are, so we can work in that realm, not in the probability realm directly. Okay. So because we had this background information and this sort of relationship that the fractions in the licensed driver pool, we might say, well, that should be a proxy. That should give us some parameter values for the probability of being an accident if the null is true. Then we can make our null hypothesis very specific here. The proportion of responsible drivers in minor accidents assigned to each age bin is equal to the proportion of all drivers in that age bin. And so we have some very specific numbers here for what we expect for each of the categories. Those come from the background information on the number of licensed drivers in each category, the fraction. And then the alternative is now the proportion of responsible drivers in minor accidents will deviate from the proportions of all drivers for at least one of the age bins. Okay, so Um, all right, hopefully that makes sense to folks, and we can move on. Um, so we collect a random sample. The researchers did this by surveying accidents where they could identify a responsible driver. They found 88 such accidents, and these were the data. 36 had the responsible driver in first age bin, 21 in the second, 12 in the third, and 19 accidents. The responsible driver was in the older age bin, the oldest age bin 4. So step 3 in hypothesis testing, calculate some descriptive statistics and a test statistic. So the descriptive statistics we could think of as sort of the proportion hat, the estimate of the proportion of people getting in these accidents now. That's not the fraction of drivers anymore. It's our best guess of what the fraction of people getting in accidents is. So there are p hats all over the place here because we're estimating these proportions. We're estimating them by what is really similar to what we did in the previous chapter on the binomial. It's the count over the sample size. So these are the descriptive statistics. All right, so these descriptive statistics are fairly straightforward. They're very similar to what we did in binomial. What about a test statistic? We've got this array of numbers. It's really not obvious what the test statistic should be in this case. The test statistic to use is totally non-obvious, and you might think, well, we have things that look like 4 different counts that look a lot like proportions. Maybe we should do 4 binomial tests. A test against x1 and a test against x2 and x3 and x4 against these null hypothesized proportions for each of those categories. I think it's worth pausing the video here and thinking about what would be wrong with doing our hypothesis test by doing those 4 tests. And the idea would be if we don't reject the null in any of those cases, then we don't reject the null overall. What would be wrong with that? I'm going to move on. And basically answer that question. First of all, these 4x's are not independent. They're all drawn from a sample of 88, and so they can't all be, for instance, in the 80s, because then you'd have more than 88 samples. So we can see that that they really are proportions of one variable that was drawn with different categories, and so we can't treat them all as independent and do just independent tests. And then, as we're going to see later in the course, conducting multiple tests in order to test one null hypothesis is dangerous, and it's difficult to do that correctly. And so doing a series of binomial tests is not appropriate because we don't have independent tests, and also because we're doing multiple tests. So we want to find a test statistic that can wrap everything up into one number that we can use to determine whether or not we should reject the null. So we're going to use the chi-square test statistic coming to the rescue here. This test statistic is useful when you have a categorical variable, summarizes counts in each category. Of course, we saw in this data set was really about age, which is a numerical variable, but we binned it into categories. So sometimes we find ourselves using the chi-square test when the raw data comes in another form, but we've put it into categories. This is a case, in this example I'm working through, where we have ordinal categories, but the chi-square test statistic actually works on nominal categories, and we're not going to use any information from the ordering from the age groups, and so it works for any categorical variable. And then the other thing you need to be able to do is you need to be able to calculate the expected counts from your null hypotheses and the sample size. So we treat the sample size as something we know, part of the study design. And so we know that, we know the null hypothesis, we need to figure out what the expectations are. And if we can do that, then we can apply this chi-square test. There's some more caveats I'm going to cover at the very end of this lecture. So what is the test statistic? So first, some notation. When we say O sub I, that's the observed counts in our data set for category I. E sub I is going to be the expected number of counts in category I if the null hypothesis is true. That's what we mean by the expectation here. And K is just the number of categories in our variable. So we had 4 bins in this example, 4 age bins, so K is going to be equal to 4. So here's the generic form of the formula. Your chi-square test statistic is a summation over each category. So I is going to index the categories going from 1 all the way up to our highest category, category K. And what we sum up is, in the numerator, this ratio. The numerator is the observed minus the expected, that quantity squared, and then we divide that by the expected value for that category. Okay? So if we think about this, what if the null were true and we have no sampling error? Of course, we're always going to have sampling error, but it's useful to think about what values of the test statistic correspond to kind of the perfect case for the null hypothesis. If the null hypothesis is true and we had no sampling error, then the observed value should be equal to the expected values. And when we do the summation, this numerator is going to be 0 in every case. So we're just summing up zeros and we get 0. So a chi-square value, a test statistic, you never actually see this, of course, because we always have sampling error. But if it were 0, that would mean there's no reason to doubt the null at all. The data looks perfectly like what we expect under the null. Okay, so 0 is the best case for the null. If we think about any deviations in expectations, from the expectations under the null, all of those are going to increase the chi-square value. And why is that true? Here's the formula again. Remember, the expectation for a category is the sample size times the proportion under the null hypothesis. That sample size and the proportion, those are always positive numbers, so the expectation itself is always a positive number. Now, it's true that observed minus expected could be a negative number, but we square that. So the numerator here is squared, so it's always going to be positive, and the expectation we said is also always positive. So they're both non-negative numbers, and that means all the terms are positive, or at least 0 is as small as they can get. So the summation is going to be a positive number. So basically, the core thing to get from this slide is any kind of deviation, because of this squaring of the numerator, is going to increase the value of the test statistic. So if we get a really large chi-square test statistic value, we're more probable that we're going to reject the null. Okay, so large numbers lead to rejection. Okay, so how do we calculate this? I recommend that when you're doing a chi-square, you fill out a table like this. It just helps you keep everything organized. So these are our categories, I going from 1, 2, 3, and 4. And they were originally aged, just if you want to connect that to the previous slides. And then down here, we're going to sum things up. So these are the observations, and that's our data for each of these categories. What about the expected? And then we can calculate the chi-square test statistic. The chi-square test statistic is going to be the sum of these terms, which are the square deviations from the expectations divided by the expectation. All right, so we just take it step by step. First step is to get these expectations. We've already talked about how to do that. We multiply the sample size by the null hypothesized proportion of the data in that category. So in this case, the sample size was 88, and 16% of licensed drivers were under 25, so that gives us an expectation of 14.08. Now, I know it seems weird. We have an expectation that's not an integer that's got 0.08. We can't observe 14.08 responsible drivers, so why is that our expectation? Remember, this is a case where statistics is using expectation in a formal sense. That means the long run average of what we'd get if we repeated this trial many, many times. So we don't throw away these extra digits here, even though we're never going to see these fractions of individuals or fractions of counts in our real data. We hold on to them in the expectations. So anyway, here we're doing that for the other ones. You see a lot of drivers in this age range from 25 to 44, so we expect around 38.72 of the accidents caused by those drivers if the null hypothesis is true, and etc. 23.76 of minor accidents caused by that next group, and 11.44. Those are the expectations if the null were true. Okay, so back to the full table. How do we go about filling this out? Well, now it's just a matter of plugging in. The observed is 36, so 36 goes there, minus the expected, 14, then we square that and divide by the expectation. So I'm showing the math down here just to sort of indicate a couple things that you can help you check yourself when you're doing all these calculations. So we set up all the observed minus the expected values in each case, and then we do that subtraction. Before we square it, actually, if you were to add up these numbers, 21.92, negative 17.72, negative 11.76, and positive 7.56, you'd get 0. Because those are just deviations before we've squared it from the expected values. And since the observed values have got to add up to 88, and the expected values also add up to 88 because we used our sample size of 88 to calculate those expectations, we shouldn't have a net excess or net loss of individuals. So those numbers would add up to 0. But of course, when we square them, they're going to all become positive, and they'll no longer add up to 0. And of course, the squaring them also makes these, it really exaggerates the differences between them. 21.92 is only a bit bigger than 17.72 in terms of magnitude, but this number is a huge difference, 480 to 314. So these cases where we have a really substantial deviation, they're going to really contribute heavily to the chi-square. And then we divide through everything, and obviously the denominators come into play here. So for instance, if we've got 57 is much smaller than 138.3, but the expectation was really small in this group, so that the chi-square term is 5.0, which is very close to 5.8 here. So everything sort of factors in how big the deviation is, but also approximately how large the expectation was. So anyway, these are how we calculate the terms, and we can see that there's a big deviation here in the first category. But those are just the terms of the chi-square. The last step is to do this summation of all of them and get this chi-square test statistic of 53. It's actually 0.05 if I didn't throw away the rounding, which I rounded things in the table, but I didn't when I did the test statistic calculation. Doesn't really matter. You can round these off to the first decimal place is fine. Okay. So there's how we calculate the chi-square test statistic. It's a fair amount of work, but hopefully this makes sense, and putting it in the table allows you to check things like check that the sum adds up to, of the expectations adds up to 88, and get a sense of which categories are giving you big deviations from the expectation. So it's helpful to set this thing up in terms of a table. Okay, so there's our test statistic. That's what we're going to use to decide whether or not we reject the null. And the question is 53.05, is that a big value or not? We're supposed to calculate the descriptive statistics and the test statistic. We did the descriptive statistics pretty easily. 53 approximately was our test statistic. Now we've got to do the next step, determine the p-value. What values of the test statistic are expected under the null? We already said that low values, closer to 0, is more in line with the null. How does the observed test statistic differ from the expectations under the null? So we're going to compare it to the null distribution. And then what's the p-value? That's the probability of observing the value of the test statistic as extreme or more extreme than what we actually observed if the null hypothesis was true. Well, what's the null distribution here? This is one of these difficult distributions that we wouldn't expect you to derive, but fortunately some statistician has already done that for us. The chi-square is a family of probability distributions. There's more than one chi-square distribution. And what do we mean by that? It's parameterized by something we call the degrees of freedom. So each degree of freedom has its own chi-square distribution. Conceptually, it's a little bit difficult to sort of derive from first principles what this degrees of freedom idea is, and we're going to try not to get bogged down by it too much in this course. But the way I think about it, or the way I recommend you think about it, is the degrees of freedom for a chi-square is kind of the number of dimensions, the number of directions the data can go in which it could surprise you. And I'll explain this a little more in a couple slides. So how do we calculate this degrees of freedom? If k is the number of categories in our variable, the degrees of freedom is k minus the number of parameters that we calculate, estimate from our data when we're making the expectations for our values, and then minus 1. So you'll frequently see it written like this, k minus number of parameters estimated, or something like that, minus 1. To just unpack this a little bit more and hopefully make it clearer, the degrees of freedom is our number of categories, and we subtract the number of parameters that we estimate from the testing data when we're calculating, sorry, there should have been a G there, the expected values. Note here that the sample size n is not a parameter. That's part of the study design. So back here when we were calculating expected values, we were multiplying n times p, but those were specified in the null. We weren't estimating those from our testing data. We got that data, we got these numbers, 16% for the first age bin. We got that from a separate data set, so that doesn't affect the degrees of freedom. And so it's a little confusing point, I understand, but when we're calculating the degrees of freedom, we're looking to the extent to which we've already fit our testing data to the expectations. And if we've done some of that, then we have to subtract off some degrees of freedom. And then we subtract off one more. Okay, so in our case, we had other data, not our testing data, that gave us those null hypothesized proportions. So we didn't estimate anything from the testing data in order to get the expected values. So our degrees of freedom is k minus 0 minus 1. So that's 4 minus 1. So our degrees of freedom for this example was 3. Okay, hopefully that makes sense. Why does it make sense to have a degrees of freedom of 3? Well, as I said, you can think of the degrees of freedom for the chi-square as kind of the number of dimensions in which the data can surprise you, or the number of you know, types of data that you can observe that would surprise you. So, for instance, we can be surprised if the observed count deviates from our expectations for 1, right? We can be surprised by the value of x1, like, whoa, that's very high, or oh, that's very low. And then we can also be surprised by x2 and by x3. The data is kind of free to vary and surprise us in those 3 directions. But once we know our sample size and x1 and x2 and x3, then we can calculate x4 just by subtraction. It's going to be however many of the sample is left, right? The sample size minus the other ones will automatically give us 4. So there's no freedom for the data to surprise us, a fourth time in some sense, right? We can calculate what the fourth one has to be. And so that's why the degrees of freedom here is 3. So hopefully that makes some sense. If that doesn't, you can just rely on the formula, right? Okay, so what does a chi-square null distribution look like? This is the chi-square distribution with 3 degrees of freedom. This describes the values of the test statistic you would get if the null hypothesis were true and you were running a test with 3 degrees of freedom, right? So once again, 0 is when the null hypothesis fits perfectly. It's not a high probability that we'd have no sampling error, but low values are quite probable, and then there's really long tail out here of less probable values. And so at some point, when we get really large values of the chi-square test statistic, we say, well, the p-value is going to be really small. It's not going to be probable that we'd see data like this if the null were true. Here's what we actually observed. We actually observed, remember, our chi-square test statistic was around 53. So we can see just by comparing that, by plotting the chi-squared null distribution out, there's not much probability here, right? So we're going to have a very, very low p-value. We can't even tell where the curve is hitting because of the x-axis, right? It's so close to the x-axis there. So clearly the p-value is going to be really tiny in this case because there's not much probability that we would see something that large if this were the true distribution of the data. So determine the p-value. These are the steps that I just repeat again and again. So I'm not going to read them out again, but they were on the previous slide. And asking what is the probability of observing the value of the test statistic as extreme or more extreme if the null were true. That was that tiny number. Probability of getting a chi-square value greater than or equal to 53 if chi-square actually did come from the null distribution of chi-square with 3 degrees of freedom. Using R, I was able to calculate that p-value is this amazingly tiny 1.8 times 10 to the negative 11th, right? So almost no way we would see data this weird just by chance. Something has got to be going on. That null has either got to be incorrect or something extremely strange happened. It's hard to sort of emphasize how small that number is. Unfortunately, in this class, we're going to have to learn some about learning how to read the chi-square values from a table. And so what we do is provide you with, this comes from the back of the book, but it's also provided on exams, of this table of critical values for the chi-square distribution. So remember, the critical values are what defines the value of the test statistic that cuts off certain percentages of the distribution. So if we're interested in the alpha of 0.05 level, as we usually are, and I said we had 3 degrees of freedom, so the way this table is laid out is the degrees of freedom go down from one, increasing order as the rows, and we can look up the alpha value, the alpha that we're interested in. The critical value for the 5% level is 7.81. The critical value for the 2.5% alpha is 9.34, 11.34 if we were rejecting at the null hypothesis at the 0.01 level. Even if we go out to the 0.001 level, the critical value for 3 degrees of freedom is 16.27, right? And remember, our test statistic was 53, so it's way out here. So we can reject at a very, alpha is less than, it's got to be less than 0.001. Using these tables, we can't get the p-value exactly, but we can get a sense of how big the p-value could be. So we won't be able to tell you exactly what the p-value is using the table, but we can say, well, our test statistic is larger than 16.27, so our p-value is lower than this alpha of 0.001. So just to look at this graphically, if you have in your mind these critical values, 7.81, 9.34, 12.34, 12.84. I've got them plotted here on the graph. 7.81 there, 9.35 there, et cetera, et cetera. So this red area all the way out to here, including all of this, that would be 5%. That's the 5% tail. Ooh. And this is in yellow marks the beginning of the 2.5% tail, right? The 2.5% tail would be all the way out to infinity. And then we have like the 1% tail, and this is the 0.005, or the 0.5% tail is this blue down here. So our test statistic value is way over there at 53. So we can tell that we've got a really small p-value, right? So the table is just giving you these sort of values that people often want to use for alpha. 0.05, 0.025, 0.01, 0.005, etc. So it's just kind of noting a few key points on the curve, and then without drawing out the curve each time, we can think, okay, where does our test statistic fall within these critical values, and that tells us something about the p-value, depending on what alpha the critical values are for. And just to give you a sense of how different chi-square distributions look, this is the chi-square with 1 degree of freedom and 2 degrees of freedom. The scales here are different. Notice this goes from to 10 and this goes up to 14. So the more degrees of freedom, remember that's the more ways the data can surprise you. And if you get sampling error in there, it basically means the test statistic, even when the null is true, it tends to be larger and larger. So the critical value at the 0.05 level, so chi-square at the 0.05 level with 1 degree of freedom is 3.84. But if you have 2 degrees of freedom, it's up here at 6, right? It has to be a larger threshold to reject at 2 degrees of freedom, because we sort of expect more noise if the data can surprise you in a couple ways relative to if the data can just surprise you in one way. So these are both they're often called L-shaped curves. It's kind of a backwards L, but these curves that look like this. But all the other chi-square distributions, once you get to 3 or 4, they start to have this hump here. But anyway, it still is true that as you increase the degrees of freedom, the critical values go up. So here went from I can't remember what it was off the top of my head. I think it was 8 point something up to almost 10 for 4 degrees of freedom. So you have to use the correct chi-square probability distribution as your null distribution. You can't just ignore the degrees of freedom stuff when looking at your test statistic. Okay, back to doing the hypothesis test. These are the critical values that I pulled out of the third row of that table. So this is how we would denote them: chi-square with 3 degrees of freedom, and then comma, and it's the alpha level. And these are all, I should have pointed this out on this slide. This is only considering the right tail of the distribution, right? So even though we're doing the hypothesis test where we reject the null if the data deviates in any direction, remember the more the data deviates from expectations, the larger the chi-square value is. So we only are interested in chi-square values that are really large. These are the appropriate critical values to use. It's a one side of the distribution that contributes here. So these are the critical values for the associated alpha. That's what we can pull out of the table. We can say, well, our chi-square test statistic 53 is greater than the critical value at alpha of 0.01. So it's even more extreme. So the p-value has got to be less than this alpha value, right? So this alpha associated with this critical value here, our value's got to be further off into the tail of the distribution, so it's got to have a smaller probability level than 0.001. And that's all you could tell from the table. You wouldn't know it was in the range of 1 times 10 to the negative 11. Okay. So step 6, answer your question and report the results. In a sample of 88 minor car accidents, the age of the driver responsible for the accident was statistically different. And here we back that up with the test statistic, 53.5, the degrees of freedom, and the p-value. And if I was using the table, all I'd be able to say is p is less than 0.001. Different from the expectations based on the assumption that based on the ages of the licensed drivers. And then we'd put some citation into where we got that data. And then frequently, as opposed to reporting a bunch of test statistics, this is where data visualization comes in. We usually show this as a figure. As shown in a figure, next page, the driver's age in age range 25 to 65 had fewer accidents than expected, while the drivers that were younger or older than that range had more accidents than expected. So here's a grouped bar chart, which is a really handy way to show the results of a chi-square where we have the observed data in the filled-in bars and the expected in the light gray bars, and we can see that we have a lot fewer observations for these middle-aged drivers, but for the senior citizens and the young drivers, the observed values are much higher than their expectations. So we can interpret, because we had rejected the null, we can, we want to tell people how the data deviated from the null. And so anyway, we summarize that verbally or textually is fine. The figure really helps people see the difference. So that's often how we display these data. Okay. So one more caveat I want to mention in this video, and we're going to talk about some more uses of the chi-square in the coming videos. When the null is true, I should have put is true here. When the null hypothesis is true, the chi-square test statistic approximately follows the probability distribution that's known as the chi-square distribution. It works really well for large N, and so it's fine. But it doesn't work in all situations. If you look at your data and any category has the expected number less than 1, or more than 20% of the categories have expected numbers less than 5, right? So these are, when you're looking at the expectations, you can do this kind of analysis before you collect your data if you know your sample size. Then that means you're going to have really small denominators in those chi-squared terms, right? Remember, we divide through by the expectation, and that can give you really large chi-squared deviations even if there's only a slight deviation from the null expected values. So small denominator can give you a big term, right? And so in those cases, it doesn't reliably follow the chi-square distribution. So what we have to do is combine categories. You have to sort of coarsen our categorization of the data by making bigger bins until this is no longer true, until none of the categories has an expected number less than 1, and no more than 20% have an expected value less than 5. So we'll see an example like that on the next one, but I did want to just mention that we can't just always use the chi-square. We have to worry about sample size a little bit. Okay, that's it for this video.